Hello, today we will be observing the effects of Newton's second law by analyzing the motion of a Coke can and comparing it to a computational model. As you can see here, the Coke can has a diameter of 0.0699 meters. It's going to also be traveling across a carpeted floor. In order to observe this motion, we should first understand Newton's second law. Newton's second law states that the net force is equal to mass times acceleration. We can rewrite acceleration as the change in velocity over the change in time. We can then rearrange the equation to be left with this, where we also change delta v to vf minus vi, the final velocity minus the initial velocity. We can once again rearrange the equation, and we're left with the final velocity is equal to the initial velocity plus the net force times the change in time divided by the mass. In this model, we're going to be observing an object that has zero acceleration. This means that the net force is also going to be equal to zero. If we use our rearranged equation, we can see that that means that this part of the equation will equal 0, and thus our final velocity will be equal to our initial velocity. This means that if our observations are free of error, then our can should move at a constant velocity. Now let's go back to tracker. Using a calibration stick, we have set the diameter of the can, as stated earlier. We also can align our can based on the y and x axis. Currently, our can is going to be moving across the positive x-axis. If we were to flip the axes so that we had our y-axis here and our x-axis here, that would not really change much in our experiment. Because we're doing a one-dimensional analysis, instead we would simply be observing the change in the y position of the can compared to time, whereas now we're observing the change in x position over time. Alright, now let's play the video and observe the motion of the Coke can. The Coke can moves in the positive x direction, and using these markers, we can get values for the position of the Coke can at different time intervals, as you can see here. Tracker will then graph these data points in this graph. As you can see, the line is relatively straight with a constant slope. This shows that the velocity is also relatively constant. Now let's view our computational model in VIDLE. In order to make this a correct and accurate model, we need to make sure we enter a couple values for our can. First, let's enter the mass of the can, which is 0.38 kilograms. Next, we want to enter the initial position of our can, which in this case is 0.001, 0, 0. This can be found by looking at the first point in tracker. Next, we have to compute the average velocity of our can. In order to do this, we have to look at the change in position of the can over the change in time using two data points from tracker. In this case, I chose two data points, and we're going to do 0.777, 0, 0, minus 0.001, 0, divided by the change in time, which is 0.791 minus 0 seconds. Our average velocity comes out to be 0.981, 0, meters per second. Now we can go back to VIDLE to view the rest of our code. First, we need to determine a value for delta t. This is the time step of our computational model, and it's going to determine how often we will measure the new position and new velocity of the can. Because our observational time is 0.957 seconds, we want to make delta t quite a bit smaller. In this case, 0.01 seconds should work well. Next, we have the while loop. This is most of the code. It starts with a condition saying that keep running this code as long as the time does not surpass the observational time. Then we have to set the vector of our net force equal to 0, 0, 0, because we're assuming that there's no net force acting on our can. Next, we have to update the velocity of the can. This is going to be the final velocity of the can equal to the initial velocity of the can plus any change to velocity. However, remember that this part of the equation is going to be 0 because our F net force is going to be 0. Next, we update the position of our can. The final position of our can is going to be equal to the initial position of our can plus the velocity of the can multiplied by delta t. This is how far the can moves in the small time interval. Finally, we have to advance our clock and show that after each time this loop runs, time is going to advance, and then we're going to have new values for the position of the can. Now we can view this model, and it will show that we have our can moving to the right and a very straight line showing that there is in fact a constant velocity. We can also compare this to our graph in tracker. As you can see, they're quite similar. However, our computational model's graph has a much straighter line because it's free of human error. Now, let's directly compare our results in an Excel spreadsheet. To the left, we have data imported from our computational model, and right next to it, we have data imported from Tracker. If we look at our graph, we can see that there are inconsistencies between the observed data in orange and the computational model in blue. At first, the computational model overestimates, and then it underestimates. Most of this is caused due to human error, as I had to use my best judgment when placing markers in Tracker, and I could not perfectly roll the can at a constant velocity. Forces other than the initial push acting on the can are gravity, drag, and friction. These forces mainly cancel out, resulting in a net force of approximately 0, meaning that our computational model gives a relatively good prediction of the can's movement. This also illustrates that Newton's second law is quite efficient and can be used to predict an object's future motion.